Good afternoon and welcome everyone to Rhode Island ASCE's presentation today, which is on Has performance-based earthquake engineering broken the power law? And today we have with us Dr. Thomas Heaton. He's the Emeritus Professor of Engineering Seismology at the California Institute of Technology. He has joint positions in the Division of Engineering and Applied Science and with the Division of Geological and Planetary Science. He's a past director of Caltech's Earthquake and Engineering Research Laboratory. Dr. Heaton's research has fallen into two broad topics over time: understanding the physics of earthquake ruptures and then understanding the impact of large earthquakes on U.S. cities. His current research on earthquake physics focuses on bridging the gap between the laboratory observations of dynamic fault friction and large-scale rupture of the Earth's crust. This requires the development of statistical physics of highly nonlinear dynamic systems. Although he was originally trained as a physicist, his career took a new direction when he joined the civil engineering department at Caltech. And I was excited about understanding this because actually my first degree is actually in physics before studying civil. Most of his research has been on understanding dynamics of different types of buildings. He has shown that although tall buildings can be expected to perform well in moderately sized earthquakes, they may experience severe damage and possible collapse in large earthquakes similar to that of 1906 San Francisco earthquake. Dr. Heaton is also a pioneer in the development of automated systems to react to an earthquake during the time between its origin and the onset of strong shaking at a particular site. Lastly, he's currently a co-principal investigator on the Shake Alert project of the California Integrated Seismic Network. I'm happy now to present to some and introduce to you Dr. Thomas Heaton.
Great, thanks so much. Good morning from the West Coast and good afternoon to you in Rhode Island. It's nice and sunny here. And anyway, this is kind of a complicated talk, so I'm going to go as fast as I can to get through it. Try to stay up. The title of the talk is Has Performance-Based Engineering Broken the Power Law? And this is a debate that I had with Dr. Alan Cornell for at least a decade when the Earthquake Center at Berkeley was first started. And the question was what to focus the research on at the Earthquake Center. And I argued that we should first and foremost understand what happens in infrequent large earthquakes because we don't understand them very well. And Alan argued that who cares about those infrequent earthquakes because they're not the main actor in earthquake damage. It's the more frequent magnitude 7 earthquakes that are the most important. So he argued that we could deal with those magnitude 7 earthquakes using probabilistic methods. And I argued that, well, if the most infrequent things are the most important, you'll never be able to use statistics. And that's the subject of this talk. And I'll argue to you that at least for tall buildings and base isolated buildings, that it's the infrequent events that are the most important. I've had a number of students work on this with me over the years, but my most important collaborator is a structural engineer, Professor John Hall, who's now emeritus as well, who taught me everything I've learned about structural engineering. So, let me give the summary first so we know where we're headed here. So I will talk about high frequency ground motions that I will characterize with peak acceleration. You've probably seen this parameter through the years. And peak accelerations typically are controlled by high frequency shaking, the frequencies greater than 5 hertz. And I'll argue to you that those high frequency ground motions, when we look at them in strong earthquakes, that they saturate with magnitude, that once you get above magnitude 6, high frequencies are no larger for a 8 than they are for a 6. And that if you look at the statistics of the high frequency amplitudes, the saturation means that we can simulate the the probabilities of those motions using standard statistical models, log normal statistics in particular. And this is the kind of statistics that's used in the insurance industry for life insurance for things like heart attacks. You could use them for murders and the like. It's another lecture to talk about why they work so well. They're fairly simple and they make statistics easy. And basically, if it is a normal distribution, all you really need to know about normal distributions are the mean, which in our case is a rate, and a standard deviation. That's what determines a normal distribution. But low frequency ground motion statistics, the part of the ground motion which is best characterized by, say, the maximum amount that the ground displaces during the shaking, those are characterized by heavy-tailed power laws, which is a different kind of statistical distribution, which is the distributions you see in epidemics like bird flu, or I made this slide prior to COVID. Obviously, COVID's changed everything. Power laws work for wars. They work for all kinds of, they work for storms, believe it or not. And they have very different kinds of statistical properties. And I'll argue to you that when you get in really strong shaking, there's absolutely no correlation between the peak high frequency motion that you see and the peak low frequency motion that you see. They're unrelated to each other. And so in the United States currently, in probabilistic design of tall buildings, which are long period structures, and base isolated buildings, also long period structures, we use design motions currently that are smaller than is widely accepted within the geophysics community. But since engineers and geophysicists don't actually talk to each other, they go to different meetings and speak a different language, most people don't really understand that this difference occurs. So here are the key issues. Although ground motions can occur at any distance and be damaging, I'll concentrate on what happens close to the earthquake rupture, within 10 kilometers of the rupture. It just makes everything much simpler. And it's those close-in motions that are the most violent and damaging. And if you look through our history of high-rise buildings, it's a pretty short history. Same for base isolated buildings. I mean, high-rise buildings, less than 100 years, base isolated, less than 30 years. Up to now, we've not experienced any large, long period ground motions where the ground moves more than a meter. And so those systems have worked well but sometime in our future, and I can't tell you when, they will have large ground motions. It's inevitable. That's the way Earth plate tectonics works, is big earthquakes have big slips. And the question that I'm going to ask is statistical prediction of those long-term ground motions actually technically feasible? And I'll argue that maybe we could do that, but we're certainly not doing it now. And it will look very different from what we're doing for short period ground motions, which is basically what the current procedures are. And my real question is, 100 years from now, will tall buildings, long period buildings, be designed differently than they are now? And I think the answer to that will just depend on whether or not we have some large earthquake in a city. If we have a large earthquake in a city, no one will pay any attention anymore to performance-based engineering. They'll just say, fix that problem. What were you thinking? And we'll have completely different way to approach things. So I apologize. Probably some of these next slides are overly simplistic for you, but let's go through them anyway. So current building codes, building codes are mostly a bunch of rules based on the type of building you're looking at and what kind of seismic zone you're in. And those rules have been developed over lots of decades of looking at earthquakes and how buildings did in those earthquakes, and then fixing things that showed up in forensic studies of the past earthquakes. And when you look at a building code that's built in that way, in essence, you don't really need to know anything about the earth. You just say, here's what buildings worked well, here's what codes worked well. You don't really need a seismologist to tell you what's about to happen. So that's been sort of the way building codes were done in the past. But starting especially about the year 2000, performance-based earthquake engineering became popular. And performance-based engineering says, design your buildings according to a statistical model of hazard. So make a model of what's the probability of things happening. And currently the practice is to build so that the expected time between collapse of buildings is 2,500 years, which for most human beings is kind of the duration of written human history. Might as well be infinite, but it's an extremely long time. But curiously, it turns out that the time for design for performance-based engineering in San Francisco is 1,500 years. And that's a little clue to tell you about what's actually going on here. The reason it's different is because San Francisco's closer to the San Andreas Fault. If you actually built the 2,500 years, you'd have to make buildings significantly different than we have in the past. So the definition of what's acceptable was changed just for San Francisco. Some people claim it correlates with IQ of the earthquake professionals in San Francisco, but I don't know anything about that. So when performance-based engineering was originally developed, it was advertised as a way to motivate owners of buildings to build to a higher standard than was being used at the time when it was first developed, which at that time now would be the International Building Code, or at the time that we went to performance-based engineering, it was the Unified Building Code. And performance-based engineering is utilized in connection of in construction of high-rise buildings mainly, and people use it because they could use the standard code, but they use performance-based engineering because it typically reduces the cost. That's the way things happen currently. So although it was advertised as a way to get people to design more expensive, taller buildings, it's now used because it costs less than to meet the standard code. So you can either use the standard code or you can use performance-based engineering. And it's become common to use performance-based engineering. All right, this is just a kind of a background slide showing a few terms I want to use. It's just a cartoon. It shows on the vertical axis is the load on a building. This would be an acceleration on the side of a building. And on the horizontal axis is the deflection. And there's it goes from 0, 0 and a linear line. You increase the horizontal load, the building deflects laterally up on a straight line that's linear, and that's the elastic range of the building. And then you get up to load we call the yield of the building, and that's this yield. And then for many buildings are designed to be plastically ductile, which means after they yield, they have the same load, even though they're deflected into the damaging area. If you decrease the load, the building should come back down on a linear line. If the building actually starts to decrease its load, then we call the system brittle, and ductile systems are better always. So just to remind you, there are all kinds of different kinds of building types, but the most common are shear wall construction. Often these are buildings up to about 7 or 8 stories. We've got lots of these at Caltech. Probably the best of them are just simple concrete boxes with holes for windows and doors. These tend to be very high yield strength, very high mass, very stiff buildings. At the other end of the spectrum are frame buildings where we've got columns and beams. And these buildings tend to be used for tall buildings, and they're much lighter and more flexible than the shear wall buildings. You can go in between and put some braces, but I'll mainly talk about these two end member classes. And so when you go to design a building, often the question is, are you designing a flexible building or a strong building? So if you have a stiff building like the shear wall building, since it tends to be since it's very stiff, it makes very high stresses when you try to deform it. It has to move as a unit. And so since it has high stresses, you have to make it strong. And but if you make it strong, it tends to increase its stiffness, which increases the stresses, which increases the required strength. And it's kind of a vicious circle. If you go to try to make a building strong, you better make it really strong. And people used to think there was a kind of a height limit on buildings because they couldn't build buildings strong enough to take the stresses in earthquakes. But then it was discovered you could make it go the other direction and make the building flexible. And when it's flexible, I'll show you in a second, it decreases the stresses in the building. But that's another vicious circle. If you make it, the more flexible you make it, typically the lower is the yield strength of the building. And so you can make it flexible, but you'll pay a penalty with the yield strength. Tall buildings, like I say, are typically always designed to be flexible. It's hard to make them strong enough. It's interesting, in Chile, they have never really gone with this principle, and they have very stiff tall buildings. Now they're going up to 65 stories, which is, I don't know what they're up to, but anyway, although if you go to the building code, there's only one building code, like the UBC or the IBC, but it turns out it's as if there's two separate codes. Once you decide it's either you're going to go the stiff route, then you follow a certain set of procedures. If you go the flexible route, you follow a different set of procedures, and you'll end up with different buildings. So here's an example of shear wall stiff construction. And this is, these are some buildings in Japan, Niigata, Japan, after an earthquake in 1964. And you can see they're concrete boxes. Architects hate these buildings. You can see that the earthquake caused failure of several of these buildings, but the failure was actually liquefaction of the foundations of these buildings. And the buildings themselves were fine. They capsized in the earthquake, and people continued to live in these buildings after the earthquake. They used the doors for windows and windows for doors. And then I'm told these buildings were actually jacked back up and are still in use today. This is an example of extremely stiff, strong structure. And here's an example of just the opposite. These are three identical steel frame flexible structures in Mexico City in 1985. And you can see one of them has had what we call a side sway collapse mechanism and collapsed off to the left here. Here, these two other identical buildings are still standing. The one on the right didn't have any apparent damage on it. The one here in the middle, if you hung a rope from the roof down to the base, you'd find that the roof was permanently displaced by about a meter. So it's got a permanent bend in it. Actually, all three buildings were later destroyed. So, but in it, there's something interesting here. It kind of tells you, if you were going to predict what's going to happen to these buildings, they all had virtually the same ground shaking. And it's, you have three very different outcomes. It just tells you how hard it is to actually reliably predict the outcome of collapse of buildings. It's not an easy thing to do. Now I want to show you some ground motion from an earthquake we had in 2010 on the U.S.-Mexican border. This was a magnitude 7.2 earthquake. We call it the Cucapa El Mayor earthquake. And the earthquake is along this fault line here. Here's the U.S.-Mexico border. Here's the city of Mexicali. And here's the ground motion record for this earthquake. It's this record is about 30 seconds long. And actually, it turns out there are two earthquakes in here. One, it started with a magnitude 6.3, and quickly a larger earthquake happened about a magnitude 7.2. And you can see there's lots of high frequency shaking in here for maybe about 30 seconds between these two earthquakes. And then later is something more subtle in this acceleration record, this kind of wavy wave that we as seismologists would call a love wave. And so, by the way, this geometry is very much like the Haitian earthquake situation. I'm going to show you a video now from downtown Mexicali. And this is, in the background is an 8-story shear wall building. And here's a surveillance camera on a pole. And you can see the earthquake starting, and the pole's probably about resonant period of maybe 2 hertz here. You can see it shaking back and forth in that high frequency shaking part of the record. So I'm sure you'd be excited. This is what you'd feel mainly if you were standing there. And pretty soon we'll get through the high frequency and get to the low frequency part of the shaking. So now we're getting to the part where the low frequencies are coming in, that love wave. And you can see how dramatically different the physics of the low frequency is than the high frequency. And that 8-story building was fine, but that low frequency motion would have been dangerous to a tall building. And this is just to illustrate the difference between high frequency and low frequency. And I just want to point out that this is an infinity pool from a high-rise building in Singapore. And I just sort of pointing out, architects are often not really thinking about earthquakes. I don't think you'd want to be in this infinity pool for the kind of motion that we saw in Mexicali. All right, so Mexicali is this city of 1 million people right next to this earthquake. It's not a wealthy city, and the geometry is a lot like Haiti. But it turns out when this earthquake was over, there were 2 fatalities out of a city of 1 million. So, wow, they did fantastic. I mean, how did a poor city like that do so well? Well, it turns out in Mexicali, Cemex, the company that does cement in Mexico, had been teaching all the residents how to make a concrete block construction, just simple concrete shear walls with reinforcing in them and filling the void spaces. And that construction style is very similar to what you would see for a 7-Eleven store. And I can tell you from living in California for years, 7-Elevens are everywhere above every big earthquake. They're indestructible, but they're certainly not expensive or hard to make. So sometimes people say, well, you couldn't possibly make an economical earthquake resilient building. Well, that's just not the case. Of course, architects hate those buildings. So here's just a photo of a steel moment resisting frame building. It's a lattice work of columns and beams. And the columns and beams are connected to each other by these flanges and welded the flanges together. This is called a moment resisting connection. You could connect all these columns and beams with just a simple connection, which is kind of, you could connect them as if there were door hinges in there, but it wouldn't work very well. So the principal thing about a frame building with these moment resisting connections is that when you deflect the building horizontally here, you get a flexure of the beams, the horizontal beams. And that flexure of the horizontal beams is a kind of spring that wants to restore the building back to vertical. And you won't get that flexure unless these connections at the beams and columns remain perpendicular. So that's that welded moment resisting connection that's critical to the operation of these buildings. The building actually would collapse if you get what's called a plastic hinge in the column of the building, primarily at the base of the building. And I'll show you that in a second. So here's some records from a tall building, a 50-story frame building during the 1994 Northridge earthquake. And along here are accelegrams taken at different points in the building and all on a common time scale. And you can see here in the acceleration, there's kind of a pulse in the middle of the record here. This is where most of the force happens during this earthquake. And you can see this pulse going up the height of the building, gets up to the top, and then it reflects and comes back down. You can see actually measure the speed at which this pulse is moving up the building. That's kind of the shear wave speed in the building. And it's about 150 meters per second, 100 meters per second, something like that. And it turns out, if you want to know what's the maximum shearing, the strain and the shearing in the building, it turns out to be the horizontal velocity of the floor, the ground motion, divided by the wave speed as the building goes up. So if you get a horizontal velocity that's a meter per second and a wave speed of a meter, you get a strain in the floors of about 1%. 1% is large enough to actually cause yielding of the structure. So that's one way to look at this problem. So in steel buildings, it's desired that these steel connections should always be perpendicular. And if the forces get large enough, they're designed to yield plastically in the beams. You don't want the yielding in the columns because the columns always have to carry the weight of the building. But if you're going to have any kind of inelastic motion, you'd like it to be in the beams, since the building can have yielding and still survive. So this is what's the desired behavior of a building. But what people found was that when you look at real buildings, no one's ever actually observed this kind of yielding that was done in the laboratory in a real building in a real earthquake. And instead, what happened was a great shock. People went out after the Northridge earthquake and found that there was no yielded steel, but there were fractured welds in any place that they looked where they expected yielding. They went back to the laboratory to see if they could reproduce that. And this is some tests that were done at UC San Diego by Cha Meng Wang, one of my colleagues down there. And this was a large project, SAC project, to study this issue. And I'll show you in here this vertical beam connected to a reaction wall, column reacted to reaction wall, forcing a beam up and down. And it's meant to simulate the Northridge earthquake. And so here's the RAM over here. Here's the column. It's forcing up and down and putting a torque on this connection. And here's the fracturing of the weld. And you can see there was never any plastic yielding in the beam as intended. And so people discovered that the connections they'd been using up to the time of the Northridge earthquake were actually deficient. It would be another long talk to talk about exactly what was going on here and how to fix it. Here's just a close-up of that connection failure. Bang. So what you can see, once it does fail, this connection is now basically just a simple hinge. I mean, it has no torque resistance, and it's a huge problem for these buildings. So in order to better understand this problem, my colleague John Hall made, and his students made some pretty sophisticated finite element codes that would deal with large deformations of steel frame buildings. And he tested those against a variety of different cases. One I'll show you is something called U20. U is for United States, 20 is 20-story. And the building that he looked at, he designed for the 1964 UBC for Los Angeles and San Francisco. It's a 3.5 second free period of this building. He also designed buildings to the Japanese building code, the same building, but used the Japanese building code of 1992. The Japanese building code is written very differently than the US code, but when you're done, it ends up with a stiffer building that's got higher yield strength, and it's got a 3 second period. And it's this code ends up being similar to our International Building Code, IBC, with the highest near source factor. So this is kind of the similar to the best we're doing in the US. And for both of these buildings, there are cases where the welds are assumed to be perfect. They never fracture. And then there are cases where the welds fracture similar to what was actually seen in real earthquakes. And by the way, in Japan, the Japanese building code is more conservative, but they typically exceed their building codes. That's because the construction companies there tend to maintain identity and ownership with buildings throughout their lifetime. It would be a tremendous economic blow for one of their buildings to be badly damaged in an earthquake. So they do everything they can to avoid that situation. So anyway, here's those buildings. There's two sets of buildings in here. There's 20-story buildings. That's these U20. And then there's 6-story buildings in here as well, U6. And these are pushover curves. These are similar to what I showed you in the beginning. The vertical is the horizontal load, and here's the horizontal displacement. And there's solid lines in here. These are buildings with brittle welds in the simulations. Then there are dotted lines, which are buildings with perfect welds in the buildings. And you can see, first off, 6-story buildings, here's the elastic part. The 6-story buildings are much stiffer than the 20-story buildings. So that sort of goes back to my comment about you can go to higher strength buildings, but you end up with more stiffness. And then the least stiff buildings are these 20-story buildings. And you can see the US code building with 20 stories with perfect welds. The yield strength of the building is about 8 or 9% of the weight, which means if you took the building and you tilted it by about 10 degrees, that would be enough horizontal force for it to begin to yield. And once it began to yield in a tilt, it would go over at about 2 meters of displacement on the roof, and then it would have a side sway mechanism collapse. Just see if I can get my pointer back. So here's where it collapses. 2 meters is about the maximum. And if you put in brittle welds, then the US one begins to yield at about 5% of its weight, and it would collapse probably within about a meter of displacement. You just couldn't catch it from in here. You can see these little jiggles in here. That's because this is an entirely dynamic analysis, and every one of those jiggles is a fracture of a weld in the system. So every time a weld fractures, it sends a shudder through the structure. You can see that in here. Notice the Japanese code building, this one in red, is up at about 14% of its weight for its yield strength. That's their higher strength and higher stiffness. You can see that in this curve here. So I'll mainly be looking at this 20-story building and also some at the 6-story building. So this code, it's a special code, and it was especially designed to keep track of what happens to the building in large deformations. If you get enough horizontal deformation, then gravity wants to bring the building down. So ultimately, you've got to have a mechanism to collapse it. In this case, it's a side sway story mechanism. And in these buildings, whether it's Japanese or US, 2 meters of roof displacement. Once it gets 2 meters, that's enough that you're going to have a collapse of the building. And just to remind you that almost all buildings in the US built before 1995 have brittle welds. This is not a problem that's been fixed. The newer buildings don't have brittle welds, but all the older ones do. So here's just how it collapses in the earthquake in this situation. So this is the frame of the 20-story building at time equals zero. We're going to see it displace the ground to the left by 2 meters, about 1.8 meters. And here the ground is moved 1.8 meters to the left. And the top is trying to catch up with the base. So the base is preceding the bottom. And you can see these little triangles in here in the model. Those are fractures in the welds of this building. And now at 7 seconds, the base is starting to move back towards, it's a pulse that goes over and back. The base is starting to move back, but the top is continuing to move to the left. And at 8 seconds, the base is almost back. By 10 seconds, the base is back, but the top just continues to move to the left and collapses. So that's the collapse mechanism in this model. So we took that model and we ran it through ground motions that we think are similar to what happened in the 1906 San Francisco earthquake. Of course, we didn't have any strong motion records from 1906, but we do have lots of data about offset of the ground from geodesy, from surveyors. So we know what the slip on the fault was, and we know a lot about how faults slip in earthquakes. And we made simulations of what the ground motions would be like on a finite element grid, and then ran those 4 different buildings through those simulations. And then this is the plot, the colors in here are the maximum drift of the building. And basically anything that's up in the red here signifies collapse of the building. So on the left are Japanese code buildings, and the top are perfect welds. I'm sorry, on top are the brittle welds, and on the bottom are the perfect welds. So kind of the worst of those buildings was the US code with brittle welds, and you can see huge areas of where you'd expect collapse of that building. And the same is true for the Japanese building. It's better, but the brittle welds really affected as well. The best is the Japanese code with perfect welds. But even with perfect welds, the US code building shows lots of collapses. It's interesting, this simulation only considers up to soft rock sites. There's no bay mud or amplification due to the Bay Area sedimentary deposits. So it's probably worse than what you see here. So it says severe damage or collapse in many areas. And the stronger, stiffer buildings do well. Brittle weld buildings are 5 times more likely to collapse than the perfect weld buildings. And we ran a similar simulation for a magnitude 7.3 on a fault we all fear in LA. It's called the Puente Hills Blind Thrust Fault, runs right beneath downtown Los Angeles. And again, we put the buildings everywhere above the earthquake, and in the basin here is where the ground motions are the worst, and you'd expect to see collapse of our 20-story US code building with good welds in a large part of the LAUS, of the Los Angeles basin. So this is kind of our worst case scenario. And I certainly I hope not to live long enough to see that ever happen. We actually ran through thousands of different simulated ground motions of large earthquakes, and we looked at when we saw collapse and when we didn't see collapse. And for each one of those simulations, if we saw collapse, we made a red dot for that simulation. And you can see there are lots of red dots in here because there's 64,000 different synthetic records. And each record is plotted the maximum displacement of the record, the maximum displacement of the ground, versus the peak velocity of the ground while it's doing it. And you can see that when the velocity is more than about 60 centimeters per second, here's the line for velocity, and here's the line for displacement. It looks like you need the combination of both large displacement and large velocity to see these collapses. And in fact, you can turn this into a probability model of that same data. These are kind of separated lines, collapse versus non-collapse. This is the Japanese code building with good welds, and it seems to collapse when the velocity is more than 1.3 meters per second and displacement more than 1 meter displacement. The worst is the US 20-story building with bad welds, and it collapses with velocities more than about 60 centimeters per second and displacements more than 60 centimeters. So really you don't want to see in a city a peak ground velocities more than a meter per second combined with peak displacements of a meter. And brittle welds are a huge problem. All right, so how does this relate to what we currently do? We currently use elastic response spectrum, and it's not used too much anymore, but people still, when they talk about ground motions, they take linear motions, 5% damped linear oscillator, and this is just force displacement curve for a linear oscillator that we would currently use something like this linear line. And then people realized, well, it's going to yield and we're going to have ductility. So the ductility in the system is the displacement at which the thing collapses divided by the displacement at which it first yields. So, and that in the system, it used to be called, well, R factors, reduction factor. And people would use the response spectrum of the linear system and reduce the required forces from this linear system down to a design system for a ductile system using this R factor. It sort of makes sense, but the problem is that if you actually say the oscillator is deflecting out to this point, the stiffness of the system is the slope of the line, and the stiffness really, the effective stiffness really decreases for large displacements. And so you expect the periods of the building to lengthen when it starts to yield. But even more importantly, if there's no damping in the system, then it just goes up and down this linear line. If there's damping, then there's the area inside one of these hysteretic curves is the damping. And if you have large ductility, you expect to see large inelastic work, large damping in the system. And in fact, if you have a ductility of 4, an R factor of 4, you would expect to see the equivalent damping up near 70% of critical damping, and currently people use 5%, which is completely different. So here's an interesting analysis where we took ground motion and put it in the 6-story building to see when it would collapse. And here's the ground acceleration up here. This is 100 seconds of acceleration. It's got high frequencies and low frequencies. And we increased the size of the motion. This is a real motion. And we ran it through the 6-story building and slowly increased the acceleration, just scaled it up until it collapsed the building. And this is the motion that would cause collapse. And it'd be 68% G acceleration in this record to cause collapse. If you did this, I'm about out of time. Okay. If you did the standard thing to this thing, you'd end up with this motion here. This is the standard nonlinear response spectrum. If you used a 70% damped motion, then you end up with this basal shear out of a response spectrum. This is the plastic motion that actually caused it to collapse. And you can see these two look very much like each other. And what this is really telling us is that using 5% damped response spectrum is just completely inappropriate. We should be using 70% damped response spectrum. I'm going to stop this part because it's too complicated. So here's now where I want to talk about high frequency and low frequency motions in earthquakes. Peak acceleration is the high frequency part, and it's what we usually talk about, but it turns out it means nothing for these long period ductile structures. it's the peak displacement and the peak velocity that are more important. And if you want to know the best kind of overall predictor, it's of most buildings, it's usually peak velocity. But for the tall buildings, it's the combination of velocity and displacement. And if we look at how acceleration and velocity varies during earthquakes, here's some median motions as a function of magnitude along this scale, going from magnitude 2 up to 7.5, and at different distances. Let's just look at the black one for the moment. This is rock sites. And you can see, of course, it goes up and increase. This is right on top of the earthquake. This is 0 kilometers. It goes up to about magnitude 5, and then it just flattens out. So this is saturation of the high frequency acceleration as a function of magnitude, and it saturates at about half a G. If you do the same thing for velocity, it has a kink, but it doesn't saturate, and the same for displacement. So the displacements and velocities continue to go up as a function of magnitude. That's why we call them large magnitude earthquakes. And if you just take all the records that we have available to us, and you, for each record, you plot the peak acceleration of the ground on its vertical axis versus the peak displacement of the ground, you'll see that there's a big scatter. The two are sort of related, and they correlate sort of, but only up until you get up to this region, then everything flattens out. And these are the near source records less than 10 kilometers from earthquakes bigger than magnitude 6. And you can see that for these close-in records, there's no correlation whatsoever between the peak acceleration on the vertical scale and the peak displacement on the horizontal scale. So peak acceleration doesn't tell you anything about the long period ground motion. So here's, if you take those near source ground motions and you make a histogram of the number of data points as a function of the log amplitude of the peak acceleration, this is the histogram. It looks like a bell-shaped curve, and this is what it looked like prior to the Chi-Chi earthquake, which had lots of data, and the median was 464 centimeters per second squared, half a G. Before and after, well, actually, it was about the same before and after. And what this tells you is that, yes, the high frequency accelerations in close are a log normal distribution, and all you really need to know is this half a G and the standard deviation, a factor of 2. And that's what it looked like every time we get new earthquakes. We just get more data in here, but we get the same answer. So, and it's this feature that really makes performance-based engineering possible. But so there, we call it Gaussian statistics, normal statistics, and you can reliably deal with that distribution. Here's the same distribution for displacement, and you can see that that's not a bell-shaped curve. And here was what the median was prior to the Chi-Chi earthquake. Here's what it was after the Chi-Chi earthquake, because it added a bunch of big long period motions. And if we were to have a repeat of 1906, this is what it would look like. So if you want to predict what's it like in close to a big earthquake, well, good luck. So this kind of distribution is a power law distribution, sometimes called Pareto distributions, and they're really tough to deal with. So, for instance, Pareto distributions are for wealth in a society. And if you wanted to know what's the total money in Rhode Island, we could go here on this talk and ask what's the mean of the people, what the incomes of the people here, and multiply by the population in Rhode Island, and come up with an estimate of the total wealth in Rhode Island. You know that wouldn't work because it really depends on the richest people in Rhode Island. People have known that for a long time, that the action is in the tail of the distribution. And this is true for all kinds of problems, like how many people will die in wars? No idea. Pandemics, no way to do that. What's your stock market really going to look like in 20 years? You think you know, huh? So it turns out that in these kinds of Pareto distributions, if they're a power law, you can't even integrate them, and you can't turn them into a probability distribution function because the power laws are not integratable. And but people use normal analysis for data that comes out of power laws all the time. And let me just say, if you've got a finite number of data points, you can always find the mean or median, and you can always find the standard deviation. And then you can start to do normal statistics, even though your distribution is fundamentally from a power law. And it's a thing we see all the time. And this is part of the reason why you see in the news, people are constantly saying, why am I seeing the 100-year flood every 20 years? It's because they're using the wrong statistical model. I mean, it might be partly climate change, but they're using the wrong model in the first place. I just want to show you a really cute record from Kathmandu in Nepal. This is long period ground motion right above a magnitude 8. So this is a video surveillance camera. And you can see people walking through the square. It's going to start to shake, and everybody's going to run out into the square. Now it's starting to shake. People are running out into the square. Let's see if you can pick up when the long period ground motions come in. The ground was moving by a couple of meters here at 2-second periods. And these ground motions would demolish virtually any high-rise building on the planet. It's really amazing ground motions. I don't have time to go through that. Let me just say, right now, most of what we're doing is based on a bunch of records that we've got available to us. And we've only been taking records for basically 50 years, but there's lots of eyewitness accounts of earthquakes. For instance, in 1906, redwood trees were routinely snapped about 10 meters from their base. Redwood trees are pretty resilient to vibration. There were 18-meter slips in an earthquake in New Zealand, and just lots of amazing accounts of what it's like to be in close to a large earthquake. But there are no records of it, so they're not included in any of these 2,500-year analyses. So just to kind of get to the end here, designing for the known, the architect gets in there early, chooses the geometry, and then we define the probability that forces that the geometry will be subjected to. And the structural engineer then decides how big to make the building. Is performance-based design. There's a different way to go about this problem. It's to admit that we can't do this problem and just start with, well, what does this structure need to do? What are the functional requirements? Consider several different designs, you could even ask an architect to do that. Determine the cost of the different designs, and then just make a judgment. What are the strengths and weaknesses of the different designs? And then when you're done, figure out what the actual capacity of the structure is, and then run it by the earth scientist and say, does this make any sense? And choose the design that's the most robust. And that our real job is to find flaws in the current system and fix them. It's not to design to the 2,500-year ground motion. And improvements, any improvements you can come up with to make things better, that's good, because it's always better. One of my main lessons and things to point out is that architects need to be bought in early and make them understand that their things they design have important constraints on buildings. And this idea of telling that the public that a building is designed for 2,500 years shaking gives the message that we can compensate for any unreasonable form that the architect could dream up. It's just not true. This claim of 2,500-year ground motion, it's not an actual robust scientific conclusion. In my opinion, it's a sales gimmick. It's a way to get people to say, don't worry about it. Everything's taken care of. The real answer is we don't know. All right, I'm just going to leave this as my final part. This is a building in Seattle with this reduced section at the base. And was it really necessary to reduce the section at the base? I mean, whoever thought this up? This was done before anybody realized, by the way, that there can be magnitude 9 earthquakes in this part of the world. So that's the end of my talk. Sorry, I went the full hour here. So thank you.
Trying to see if do we have time for any questions at this point? I can't hear you, Chad. Sorry.
Sure. I think we got time for a couple. Leading off that last slide, I think the big question is, how are designs like that permitted?
Well, so one of the suggestions has been sort of don't allow really tall buildings. And it gets back to a very deeply philosophical question. Right now, the public wants to be told this is safe. But the answer to these, if you choose a tall building, you cannot make that statement. You can only say this building is stronger than the others. It's got a higher yield strength. It's better than but you can't say, I know the earth can't defeat this building. So, personally, I would say if it was my choice and I lived in an earthquake area, I'd say just forget the really tall buildings. It's just too difficult. But if you want one and you actually have to have one, that's your business. It's your money. But just don't tell people you know it's safe, because you don't. I mean, just be honest with them and say, this is a fantastic architectural achievement, but one of the downsides to doing this is we've left the door open to large earthquakes. And just be honest with people and tell them that. But then nobody would invest in it, right? So when we get a big earthquake, and if we lose some tall buildings, nobody's going to do things this way. NASA used to use performance-based engineering to design the shuttle. They put probabilities on all the different parts of the shuttle. And when the Challenger blew up, they realized that was just futile. There was an error in the engineering, and they just completely abandoned all that probability stuff. And they said, if there are errors, we need to fix them. We need to find them and fix them. And I think you can see that's kind of happening in this horrible disaster in Florida. I mean, let's put some probabilities on the Florida disaster. No one cares about the probabilities. They say, don't let that happen again. Don't do that.
So what you were suggesting was with the earthquakes, it's more of a chaotic behavior and more chaos theory that's being applied. Is there a model or a statistic that can be applied to that chaotic behavior, or does it need a different approach?
Actually, we're not currently using a chaotic behavior. I'm convinced from my work on physics that it's chaotic, and if we were to simulate it with chaos, we'd use power laws, which people are not using. They should. But if you're going to use a power law and you're going to say, I'm going to not have the worst case scenario, you've got to truncate the power law. You got to say, I won't allow it to be bigger than a certain amount. And sometimes people make a guess at what that amount is based on their understanding of physics. But I'll tell you, our current understanding of physics of earthquakes is pretty feeble. I mean, there are lots of papers out there, but the most fundamental of problems in earthquake physics are still highly mysterious. I mean, and all you have to do is look at what happened in Japan for the Tohoku earthquake. I mean, I told them in 2010 they should worry about magnitude 9 earthquakes, and they said, no, never. We've got thousands of years of history. It can't happen, and it did happen. I mean, we're still wondering exactly what happened. I mean,
so is there anything that can be applied based on historical performance in buildings that have performed well in San Francisco, citing those precedents in future designs? Is there means of doing that?
well, so I'm personally a fan of the buckling restrained braces. So if you make a tall building really flexible, you're opening the door ever more so for these really large ground motion displacements. So the more ductile you can make the system and the stiffer you can make the system, the better off you are. You still can't put a number on exactly what's the repeat time for failure, but you could say this building has got special measures and it's better. That's, in a sense, that's what we used to do 40 years ago. People said, oh, this is built according to this great code or whatever, and this is a better code, but nobody really gave you, we know for sure it's going to work.
Thank you.
Welcome to life.
Thank you so much, Professor Heaton. And thanks to all of our guests today who joined us for this presentation. Chad, was there one other item in terms of we were going to do in terms of a presentation with respect to some type of donation?
Yes. RIASCE has donated $100 to earthquake relief in Haiti on your behalf. So thank you.
All right. If no other questions for us, I want to thank you again, Professor Heaton, and thank your ASCE audience for attending with us. I want to thank again our president, Chad Morrison. So we know he's our president of our board of directors for ASCE Rhode Island, but he also has been serving as our producer. So I want to thank him, and I want to thank all our board members and especially our advisor, Larry Smith, for introducing us to Professor Heaton and the possibility of sharing this special presentation. So we see that we have some things that we're sharing with you, and looking forward to our next lunchtime live stream that notice will be coming out fairly soon. And thank you again for attending with us today.